For this example, we will select a number, then add 3, double the result, add 4, divide by 2, subtract the original number, and then use deductive reasoning to determine the result of this pattern. So we have the pattern described, but math people like abbreviations. They like actually being able to say this is what that whole thing looks like. And words, not usually a mathematician's best friend. So what we're going to do here is, instead of jumping straight to deduction, we're going to think a little bit inductively first. We're going to take some specific examples to try and get that general pattern that we can then use to draw out our theorem, our specific, but a little bit more general, I guess, result. Like I said, induction can feed into deduction, deduction can feed into induction. It's a matter of what information you have and what information you want to find. They're not so much opposites as they are things that sort of work in a cycle. So we want to start out here with some things that we have. Usually when we're trying to do things we don't know where to start with numbers, probably want to begin with either 0 or 1, just because they're the most manageable for almost any arithmetic. I'm going to do 1 here. So if we start with the number 1, what's going to happen here is we will take 1, then add 3. So I'm just going to draw arrows here, maybe a little bit loose with the notation. We'd get 4. Then what we're going to do is take 4 and double it. So multiply by 2, you get 8. Then the next step after that is we add 4. So you get 12. Then we will divide by 2. That would give us 6. And then last step, we subtract 1 to get 5. Obviously, there's a more exacting way we could deal with this in terms of parentheses, but I'm going to start with a very loose notation here so that we can get the idea without worrying too much about that kind of detail. So we got 5. All right, let's try another number. Let's try 2. Okay, so if we start at 2, we add 3 to 2, that would give us 5. We multiply 5 times 2, we would get 10. We add 4 to that, we get 14. We divide that by 2, we get 7, which leads me to believe that I might have made a small mistake here. Let me double check this. Oh, that's silly of me. We're subtracting the original number, not 1. Jumping ahead of myself. See, I'm moving too fast sometimes. It causes me to lose my own confidence. But we get here to 7, and then we subtract the original number, which was 2, minus 2, gives us 5 again. So we've got 2 cases here that both give us 5. And like I said earlier, 2 cases usually isn't enough to really make a good argument, but for the purposes of this video, I'm going to be brief here and say that this tells us, that our pattern will give 5 back. I'm going to leave it to you to check this again for numbers like 3 and 4. So you take 3, add 3, multiply by 2, plus 4, divide by 2, subtract 3. Similarly for 4, you should again get 5. Where this is kind of the result we get from our induction. That we've taken some specific cases and we get some general information about the pattern that it should give back 5. And then from there, if we want to be a little bit more sure about this, get our theorem, what we're going to do here is think in terms of something general using this pattern, where the most general thing we can do with a number is just take a placeholder, that is, take a variable, where for a reason that I'll get to when we talk about the natural numbers, I'm going to try this for the general number n. N in math is usually a placeholder for a nice counting number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. The nice numbers, as it were. The natural numbers, as we'll see, they're called later. So if we start with a number n, it's going to look a little bit different this time because we're going to have n's and numbers in here. You add 3, you'd get n plus 3. You then multiply by 2. Being careful with the, what's the word I'm looking for, distribution, you should end up with 2n plus 6. Then from there, if you add 4 to that, you'll end up with 2n plus 10. Then what we're going to do is be careful here and divide by 2, where again you got to distribute. Divide 2n by 2, excuse me, and you'll be left with n. Divide 10 by 2, and you'll be left with 5. So at our last step, when we subtract the original number, n, what we're going to end up getting is just 5, which tells us that for any value we want here, n, remember this is a placeholder for anything that we can put in, any whatever, not necessarily 1, 2, 3, 4, and whatever, but that's usually what we use n for, we should get 5 back. So, what we did here, what our result says, is following the deductive reasoning of using the general value n, we still get 5. So, we have our result here. We have our theorem that this pattern will give us the number 5, no matter what number we put in. This is a little bit closer to the exacting mathematical logic that we'd want to use. And I'll say that for this, we didn't technically need to use the specific cases. We didn't need to use inductive reasoning, but it did help a little bit. So when you're trying to do a problem like that, I won't necessarily require that you use the inductive line of thought to set yourself up, except maybe on worksheets where I want you to work through the steps, but it can be useful to, at the very least, give you some intuition that this is where you're supposed to end up. Because for a lot of people, especially people in your position, it might be unusual and unintuitive to just jump straight to plugging in n and hoping for the best. Anyway, this is the idea of what we're working with, and this is basically all there is for section 1.1. So we'll move on here to section 1.2, where we are going to be looking at some more concrete modeling-based ideas.